So just looking at the problem, you should anticipate a slant asymptote because you got a numerator with a higher degree than the denominator. So if you want to find all the asymptotes first, maybe, I'm going to do a little key over here. So I have vertical, horizontal, or slant. We'll find minima and maxima, points of inflection, increasing, decreasing, concave up, concave down, x-intercept, and y-intercept. Okay, those are all the things.
No, the funny thing is that we don't even have to do all these things. You just plug it in.
No. Alright, so the vertical asymptote is whatever makes the denominator 0. So in this case, that's just going to be x equals 0. And then we will not have a horizontal asymptote because we have a slant asymptote. So we're going to take numerator, I'm filling in a placeholder right there for the x term that does not exist, and then divide the denominator. So in order for x to fit into x squared nicely, we would have to multiply by x. So I'm putting that up there in the x column. Then we're going to multiply x times x, which is x squared, and x times x, oh yeah, just that. Usually you multiply twice, there's only one thing there, so you don't have to do that. Okay, so you get 0, then you bring down this guy, which is a 0x. So x times 0 would go in there, and then once you get to the constant, you stop. Now obviously we don't need to write x plus 0, we can just write x, so our slant asymptote is at y equals x.
That's when you use it.
And then if you want to think about it graphically, you can think about it like y equals 1x plus 0. So it's going through the origin, and it's got a slope of 1.
Okay.
You know how we used to reflect across y equals x?
For inverse.
Yeah.
It's like that.
Alright, so that's our asymptote. Now we need to find derivatives. So, first derivative. Okay, you have options. You can either use the quotient rule, or you can take this function and split it up into the sum of two fractions that have a common denominator, and then you can simplify those. So this would simplify to just x, and then this would be plus 4 over x. And that is easier to differentiate. Okay, or you could just use the quotient rule. So I guess I can do it both ways. So if you do this, so if you simplify first and then take the derivative, you should get 1 minus 4 over x squared. And if you use the quotient rule, you do low d high minus high d low all over low low. And simplifying, you should get 2x squared minus x squared minus 4. And then 2x squared minus x squared is just x squared. Okay, so you're here, and then you could split this one up into two fractions, and that's how we would get here. Okay, or you could just leave it. Either way, you want to try to take it instead of equal to 0. So if we take this one instead of equal to 0, when you multiply the x squared over, you just get 0. So you're solving x squared minus 4, which we know has 2 and negative 2 as the solutions. In addition to that, so if this is our first derivative, are there any values where the derivative does not exist? Zero. So on your first derivative test, you're going to include negative 2, 0, and 2. Okay, so you're including 0 because the derivative doesn't exist in there. So again, your vertical asymptotes will always be on your derivative test. Okay, so I'm going to plug it into this one because I think it's easier. So if I put like negative 3 in here, I get 4/9, which is smaller than 1, so that would make this positive. If I put in negative 1, that's going to be 1 minus 4, which is still, wait, that's negative. Yeah. And then if I put in positive 1, that's going to be like the same situation, so it'll be negative. And then over here, if I put in positive 2, it'll be positive for the same reason this guy was positive. So it's switching from concave up, or not concave up, I'm sorry, it's switching from increasing to decreasing here. It's going to decrease the whole time here, and then it's going to increase after 2.
So like,
So it's like up,
yeah, down,
down, and
stay
then
down, up.
down,
But is that a full
They're
or
probably,
asymptote?
they probably look like
Yeah.
this, because
Yeah.
remember we have a slant asymptote,
Mhm.
something like that, most likely. So okay, wherever it goes from increasing to decreasing, that's going to be a maximum. So you should have a maximum at -2. And then wherever it goes from decreasing to increasing, you'll have a minimum. So you're going to have a minimum at 2. And then where should we put those back?
The
In
first one.
the first one. So 2 squared plus 4 is 8, over 2 is 4. And then
4.
-2 is going to be -4. All right, now, so far we don't have any points of inflection. You want to make sure that you're not calling an asymptote a point of inflection. So just keep that in mind. All right, so second derivative. So we can either use, this one was our first derivative, or this one. So I'm going to use this one because I feel like it's easier. So the derivative of 1 is 0, and then this is like 4 times x to the -2. So this is like 4 times x to the -2. So that's going to be positive 8 x to the -3. So 8 over x cubed is my second derivative. You could also use the quotient rule. So that'd be low d high minus high d low all over low low. And that gives us 2x cubed minus 2x cubed plus 8x. These cancel, you get 8x over x to the 4th, which is the same thing we have over there. Okay, if you set this equal to 0, are you going to find any points?
No.
No. So there's no solution to that. So that means that your second derivative test should have what on it?
Where there's no solution.
Just 0. Yeah. So where there's no,
Oh, yeah.
where the second derivative doesn't exist, which is still 0. All right. So if we plug in like -1, the denominator would be negative. And if we plug in +1, the denominator would be positive.
Yay.
Okay, so 0 being an asymptote, you wouldn't call it a point of inflection because it's not a point, it's an asymptote. So while the concavity is changing, it doesn't make it a point of inflection. You could have possibly had a point of inflection if you had found maybe more solutions with your second derivative. All right, so let's fill in increasing and decreasing. So we're increasing up until -2, and then after 2. Okay, so from -infinity to -2, and then again from 2 to positive infinity. And we're decreasing in between those. We did our second derivative test, so we're going to be concave up after 0, concave down before 0. Okay. And then the last couple things are your intercepts. So,
So the x-intercept just
I'm
0.
gonna get rid of this guy. Alright, so your x-intercept, you're gonna take your original function, and you're gonna let y be 0.
So it's just
Nope.
no.
So if you multiply by x,
Oh, it's plus or minus 2.
nope.
What?
Subtract your 4. What's the square root of -4?
2 or -2.
Nope.
Oh, I can't. There's no such thing.
Right. It's imaginary. Imaginary numbers are not on the coordinate plane, so you don't have any. Over here.
But it's still technically plus or minus 2.
No, it's plus or minus 2i, which is not a real number, so that means you're not going to see it on the graph. So while it has solutions, they're not real solutions that you would see on a graph. Y-intercept. Y-intercept, you just plug zeros in for x. Okay, what do you get?
No solution.
Yeah, can't do that either, because you can't divide by 0.
Oh yeah.
So you don't have any y-intercepts either.
But
Makes
you can
sense
have,
since there's an asymptote.
but you
that's
can't have
like
a 0 on
keeping
the
a-
top.
There are little corners.
Exactly. So this asymptote is a vertical asymptote, keeping it from intersecting into the y-axis, and then this asymptote is kind of just keeping it elsewhere, I guess, such that it can't quite get to the x-axis. So, I guess I'll graph it over here. 1, 2,
It's been a long day.
1, 2, 3. Okay, so I'm going to graph the max and min first. So we have a minimum at 2. Wait a second. Did I mix those up?
Yeah.
Yeah, I did. I just wrote them down.
Wait, no you didn't.
Yeah, I did.
How could there be a max that's
Wait,
lower than the
no,
minimum?
you're right. You're fine.
Doesn't make any sense.
Oh wait, no, it was just before though. It wouldn't be. Wait.
Oh,
doesn't make
it makes sense in context of this question. Never mind. It doesn't make sense for a continuous function. We're not looking at continuous functions anymore,
Okay.
so it does actually make sense because when you look at irrational functions, it's almost like a piecewise function. You're looking at like 2 different pieces. So that wouldn't make sense for a rational function because your minimum would have to be like lower than your maximum for a continuous function. But since this isn't a continuous function, this is actually fine. Because your minimum is here and your maximum is here.
But
Well,
that's
and
for
it-
the thingy.
In a continuous.
When it's
oh, wait,
concave
what?
down, that's
If you're-
concave up.
What? Sorry.
Because of the concaves.
It was because of increasing and decreasing here. So.
Right.
Max
But like,
and-
no, I'm just saying like.
Oh, concavity. So it is concave
Right,
down
right.
and then concave.
Yeah,
up.
so that's like.
Yeah.
It makes sense in my brain. It's just.
Yeah. I usually put the asymptotes in here first. So there's one here along the y-axis, and then the other one is going through the origin, and it has a slope of 1. So something like this. Okay, so that's why the rest of our graph is not going through the axes, because they're stuck in here. That's not as jagged as it looks. It's curved. Pretend it's curved. I'm not tall. So yeah, they look like, kind of like
Little parabolas.
smushed, yeah, like little like slanty smushed parabolas.